Hello everyone, I am Karna from BSc Chemistry Honors Final Year. Today's my chapter is from Pradeep's Inorganic Chemistry book by Dr. K.K. Bhasin. Magnetic properties of transition metal complexes. Electrons revolve around the nucleus in every atom. A revolving electron like a loop of current was shown by noted physicist Oersted in 1820 to deflect the magnetic needle. When electron revolves in anti-clockwise direction, the current is clockwise. As a result, the upper face of electron loop acts as the south pole and the lower face acts as the north pole, as shown in figure. Thus, an electron in motion behaves as a magnetic dipole and possesses definite magnetic moment. If E is the charge on the electron revolving in an orbit of radius r with a uniform angular velocity omega, then the corresponding current produced is I is equals to charge by time equals to E by t. T equals to period of revolution of electron. E is equals to 2 pi upon omega. I is equals to E upon 2 pi upon omega is equals to E omega upon 2 pi. Area of orbit is equals to pi r square. Magnetic moment of atom is given by m is equals to I. A is equals to E omega upon 2 pi into pi r square. M equals to 1 by 2 E omega r square. According to Bohr's theory, an electron in an atom can revolve only in discrete stationary orbits, which the angular momentum of moving electron is an integral multiple of h upon 2 pi and where h is Planck's constant. MVR equals to n dot n into h upon 2 pi and represent orbit and can have values 1, 2, 3. Mu is equals to r omega m into r omega into r equals to nh upon 2 pi omega r square is equals to nh upon 2 pi m. Mu b is equals to eh upon 4 pi m. It is clear from the equation that the magnetic moment of an atom is quantized and the smallest value of atomic dipole moment m is mu b. This value of m is called Bohr magneton. The small magneton is the magnetic moment of an atom due to the orbital motion of electron in the first orbital of hydrogen atom. Since the magnetic field is produced by moving electrical charge, it is expected that the nuclear spin, the spin and the orbital motion of electrons will result in magnetic moment. The nuclear contribution is very small compared to the electronic contribution. Therefore, the nuclear contribution can be easily neglected. It means that the measured magnetic susceptibility of pure substances are usually associated with the electrons. Each moving electron can be regarded as a micromagnet and the total moment exhibited by a substance is the net result of the moment of individual electrons. To define the magnetic behavior of material, it is appropriate to understand a fifth term associated with magnetism, pole strength. The strength of a magnet may be expressed in terms of unit pole. A unit pole is defined as the pole that repels or attracts a similar pole placed 1 cm away with a force of 1 dyne. Thus, a unit intensity of magnetic field exists at the point and the unit pole experiences a force of 1 dyne. Pole strength and lines of pole force. A magnetic field of unit intensity is considered to give a unit line of force per square centimeter. If a pole of strength m is enclosed in a sphere of radius 1 cm, a total of 4 pi m lines of force will come out of this pole. This is because the surface area of sphere is 4 pi square centimeter. The number of lines of force per square centimeter as surface of sphere is given by 4 pi m upon 4 pi is equals to m. Intensity of magnetization. It represents the extent to which a sample is magnetized when placed in a magnetic field. It is defined as the magnetic moment per unit volume of magnet. I is equals to magnetic moment by volume. A is uniform area of cross section of magnetized sample. 2L is the length of sample and I becomes m into 2L upon A into 2L is equals to m upon A. The intensity of magnetization of a magnetic material is also defined as the pole strength per unit area of cross section of the material. Magnetic induction. When a substance is placed in a magnetic field of strength H in gauge or Oersted, the total magnetic induction or magnetic flux density B within the substance is given by the relationship B is equals to H plus 4 pi I. B upon H is equals to 1 plus 4 pi I upon H. B by H is equals to 1 plus 4 pi K. B by H is magnetic permeability. Magnetic permeability is the ability of a material to permit the passage of magnetic lines of force through it. The magnetic permeability of a substance is the ratio of density of magnetic lines of force within a substance in a magnetic field to the density of the lines of force in that field in the absence of this substance. The ratio of 1 I upon H is called magnetic susceptibility per unit volume or simply as volume susceptibility. It is a property which determines how easily a sample can be magnetized. It is this quantity that is commonly measured experimentally. Magnetic susceptibility is commonly expressed per gram as psi, where m is the molecular weight. It is equals to m upon d, molar susceptibility. The magnetic susceptibility is related to all the permanent magnetic moment mu b of pure substances by the relationship which is equals to molar susceptibility या magnetic susceptibility is equals to n mu square b upon 3 kT mu b square. K is equals to Boltzmann constant and Avogadro number, T absolute temperature in Kelvin. The permanent moment is expressed in Bohr magneton. Mu b square is equals to 3k upon n molar magnetic susceptibility into T. Mu b is equals to 3k upon at under root xm under root T under root 3k by n under root. Upon evaluating the constant, we get mu b is equals to 2.828 in under root of xmt. Thus, the magnetic moment can be calculated from the magnetic susceptibility using the above relation. Type of magnetic material. When a substance is placed in an external magnetic field, the magnetic field produced by the spin and orbital motion of electron of substance interact with the external magnetic field. Different substances show different magnetic behavior when placed in the external magnetic field. On the basis of their magnetic behavior, different materials can be classified into the following three categories: diamagnetic substances, paramagnetic substances, ferromagnetic substances. Diamagnetic substances. Substances which are weakly repelled by the external magnetic field are called diamagnetic substances. Diamagnetism is exhibited by substances which allow the magnetic lines of force to pass preferably through vacuum rather than through themselves. It amounts to saying that in case of diamagnetic substances, the number of lines passing through them is slightly less as compared to the lines of force passing through the vacuum. As a result, diamagnetic substances are slightly repelled by an external magnetic field. Diamagnetism is exhibited by all substances with completely filled electronic subshells. Diamagnetism is produced by the orbital motion of electrons of the atoms, ions or molecules of this substance. Diamagnetic effect arises only when the substance is placed in a magnetic field. It is due to the interaction of applied magnetic field with the magnetic field induced in a substance with completely filled electronic subshell. The induced magnetic field in case of substances with paired electron is the opposite direction to the applied magnetic field. Paramagnetic substances. Paramagnetic substances are broadly defined as substances which are attracted towards the applied magnetic field. The number of lines of force passing through a paramagnetic substance are much more compared to those that would pass through vacuum. Paramagnetism is caused by the presence of unpaired electrons. The more the number of unpaired electrons in a substance, the greater is the paramagnetic behavior. We know that most of the transition elements, including f-block elements, are known to certain unpaired electrons. As a result, transition metal displays paramagnetic character. All paramagnetic substances have a net non-zero magnetic moment of its own. Some of the common examples of paramagnetic substances are aluminium, platinum, chromium, copper sulfate, salt solution of iron, copper and nickel, and dioxygen molecules. Some of the paramagnetic substances show complicated magnetic behavior which arises due to the interaction of individual magnetic moments. The individual magnetic moment interact with another in such a way so as to align themselves spontaneously. Now table is given. Experimental method of determining magnetic susceptibility. A number of methods for determining the magnetic susceptibility are known. The two important methods are Gauss method, Faraday's method. Gauss method. The method involves the filling up of finely powdered substance to a certain height in a Pyrex glass tube called the Gauss tube. This tube is suspended from an arm of a sensitive analytical balance in a magnetic field. An electromagnetic magnet providing a constant magnetic field in the range 5000 to 20,000 Gauss is generally used. The bottom part of the sample is in the This tube is suspended from an arm of a sensitive analytical balance in a magnetic field. An electromagnet providing a constant magnetic field in the range 5000 to 20,000 Gauss is generally used. The bottom part of the sample is in the stronger part of magnetic field, while the top part of the tube is in a zero magnetic field. The whole assembly is housed inside an enclosed system in order to avoid vibration of the suspended sample. A diamagnetic representation of the setup is shown. The powdered substance in the Gauss tube is first weighed without the magnetic field and then weighed in the presence of magnetic field. In case of paramagnetic substance, the substance will be attracted strongly towards the magnetic field and will weigh more. This increase in the weight of substance is a measure of the paramagnetism of the substance caused by the unpaired electrons. The larger the number of unpaired electrons in the suspended substance, the greater is the increase in the weight of the magnetic field. In case the substance is diamagnetic, a decrease in weight of substance is registered when the magnetic is on. Calculation of magnetic moment. The Gauss method is the simplest of all the methods for measuring the magnetic susceptibility. The method measures the force exerted on the cylindrical samples suspended in a non-homogeneous magnetic field of an electromagnet. The force acting on the sample is given by the expression F is equals to half of AKH square. A cross-sectional area of cylinder, H intensity of central homogeneous part of magnetic field, K is equals to volume susceptibility. The above expression of force is applicable only if the measurements are carried out in vacuum. However, since the sample is placed in air, the susceptibility due to air needs to be subtracted from the measured susceptibility, and the equation becomes F is equals to 1 by 2 AH square K minus K dash, where K dash is the volume susceptibility of air. The Gauss tube itself is in the form of hollow specimen and exert a force which is always present. In order to evaluate the exact force acting on the sample, the force developed due to hollow specimen needs to be subtracted from the measured force. The force acting on the hollow specimen lambda is negative because the tube is made up of diamagnetic material, and equation is further modified to F is equals to 1 upon 2 AH square K minus K dash plus chemical shift. इसको बोलते हैं हम डेल्टा. This is equals to force developed due to hollow specimen. For a specimen of constant length and cross-sectional area, the factor H square is equals to constant if we take into consideration the density of specimen equals to alpha plus beta dash f upon omega. 10 is equals to 10 raised to power 6 x. Alpha constant for displaced air and is equals to 0.029 into volume of sample. Beta is equals to tube calibration constant. Omega is equals to weight of sample expressed in grams. F dash is equals to force on the sample. Gauss tube is calibrated by filling the tube with the substance whose susceptibility is accurately known. The commonly used substance for calibration is deep blue colored compound mercury tetrathiocyanatocobaltate. Its susceptibility at 20 degrees Celsius is 1.644 into 10 raised to power minus 7. Paramagnetic susceptibility is equals to magnetic susceptibility minus diamagnetic susceptibility. Some of inherent advantages of Gauss method are: it requires very simple, easy to assemble equipment. It is reasonably priced equipment. It is easy to handle and use. It requires a large amount of substance. Thus, an ordinary analytical balance can be used to measure the change in mass. Disadvantages of Gauss method. In spite of several advantages, Gauss method suffers from the following disadvantages. It requires large amount of sample. Uniform packing of sample in Gauss tube is not only tedious and time consuming but is very laborious. Consistent results are not obtained if the packing of sample is not uniform. Faraday's method. Faraday's method requires a very small amount of magnetic sample. The sample packed in a quartz ampule is suspended from a sensitive balance in a region of fairly strong magnetic field as shown in figure. The sample is suspended between the magnetic poles so that the value of product H dH upon dx is constant over the region occupied by the sample. dH upon dx is the gradient of the field. The whole setup is enclosed in a closed system which can be flushed with inert gases like nitrogen or helium. A sample weighing 0.1 to 10 mg of the substance taken in a ampule of internal diameter 1 mm is placed in a magnetic field of constant gradient dH upon dx. The force acting on the sample is measured directly using a quartz fiber torsion balance and is given by F is equals to mxh dH upon x. M is equals to mass of sample, x is equals to susceptibility of sample, h equals to intensity of central homogeneous part of field, dH upon dx is equals to gradient of field in x direction. Similarly, the force exerted by standard calibrant can be measured by weighing the calibrant both in the field and out of field. Generally, the calibrant used is mercury tetrathiocyanatocobaltate. Second, since the magnetic field H and the field gradient are the same in case of unknown sample and the standard, the force acting on the sample and the standard can be written as H dH upon dx is equals to F upon mx for unknown sample, and for standard H dH upon dx is equals to Fs ms xs. On rearranging x is equals to F ms into xs upon Fs dot m. X and xs are susceptibility of sample and standard. M and ms are respective masses while F and Fs are respective forces at constant H into dH upon dx. Advantages of Faraday's method. Faraday's method requires very small quantity of substance and the sample need not be homogeneous. Compared to Goel's method which requires large amounts, 1 gram, this method requires only several milligrams, 10 mg. Faraday's method gives the specific susceptibility directly. On the other hand, Goel's method gives volume susceptibility in order to convert volume susceptibility into specific susceptibility. One needs to know precisely the density of the sample. It is difficult to determine precisely the density of solids because the values of density depend upon the packing of solids. Disadvantages of Faraday's method. The main disadvantages of this method are the equipment is very delicate and requires great manual skill. Since only a very small amount of the sample is used, reactions occurring at the surface of sample will lead to large errors. Relationship between magnetic susceptibility and magnetic moment. The magnetic susceptibility is related to magnetic moment by the relation Xm is equals to n naught mu square upon 3 kT. N naught Avogadro's number, K Boltzmann constant, T is equals to absolute temperature. 6.023 into 10 raised to power 23 is the Avogadro's number value. On rearranging these equations, we found mu is equals to 2.828 into under root of Xm into T. Variation of magnetic susceptibility with temperature, Curie and Curie-Weiss law. We have learned that magnetic susceptibility varies with temperature and is therefore temperature dependent. It was shown by Pierre Curie that the paramagnetic susceptibility varies inversely with temperature. Xm is directly proportional to 1 upon T. Xm is equals to C upon T. C is equals to constant characteristic of substance known as Curie constant and T equals to absolute temperature. The above expression stating paramagnetic susceptibility vary inversely with temperature is called Curie's law. A large number of paramagnetic substances obey this law, especially at high temperature. If we plot a graph between Xm and absolute temperature T Kelvin, a parabolic curve is obtained. However, if we measure Xm for a substance at several temperatures and then plot 1 by Xm values against absolute temperature, a straight line with slope C is obtained, which intersects the origin. Curie's law is followed by substances where there is no spontaneous interaction among the adjacent unpaired electrons. In other words, there is no secondary magnetic interaction between the neighboring magnetic centers. Such a substance is called magnetically dilute. Although a large number of substances displays this behavior, many substances give straight lines that do not pass through the origin, rather intersects the temperature axis a little above the 0 Kelvin or little below the 0 Kelvin. Such compounds are stated to obey modified Curie equation, according to which Xm is equals to C upon T minus theta, where theta is the temperature at which the straight line cuts the absolute temperature T axis. This modified equation is called Curie-Weiss law. Theta is known as Weiss constant. Taking into consideration Curie-Weiss law, the magnetic moment can be calculated by the equation. Mu is equals to 2.828 into under root of Xm T into T minus theta, Bohr magnetone, Bm. Ferromagnetism and antimagnetism. We have learnt that the magnetic properties in case of paramagnetic substances originate entirely from the individual magnetic centers. It means that there is no secondary interaction between the neighboring magnetic centers. Such type of substances are named as magnetically dilute substances. However, there are some paramagnetic substances in which secondary magnetic interaction exists between the neighboring magnetic centers. Such substances are called magnetically concentrated substances. In such cases, the magnetic susceptibility shows dependence on both temperature and field strength. Two such important type of magnetic substances are ferromagnetic and antiferromagnetic. The dependence of susceptibility of these two forms are displayed. A close inspection reveals that there is some discontinuity in the curve at a temperature marked Tc on the curve. This temperature is called Curie temperature. Above the Curie temperature, all ferromagnetic substances obey Curie or Curie-Weiss law. In other words, above Curie temperature, the ferromagnetic substances behave as simple paramagnetic substances. However, below Curie temperature Tc, the magnetic susceptibility behavior is different and depends upon the field strength. A close inspection of figure reveals a characteristic temperature Tn called the Néel temperature. Above Néel temperature, it is all antiferromagnetic substances follow Curie or Curie-Weiss law and show simple paramagnetic behavior. It is important to note that below Néel temperature Tn, the magnetic susceptibility decreases with decreasing temperature. It is important to remember that entire magnetic substance has its magnetic susceptibility independent of temperature. Magnetic moment. An electron has two types of motion associated with it. One of it is going around the nucleus in an orbit while other is spinning about its own axis. Since electron is a charged species, its movement generates a magnetic field. The electron determines the magnetic property in two ways. The magnetic moment associated with motion of electron around the nucleus is called the orbital moment, while magnetic moment associated with the spinning of the electron on its own axis is called the spin moment of the electron. The resultant magnetic moment is the sum of the orbital moment and the spin moment of the electron. We have already discussed that the magnetic moment of substances are generally expressed in terms of unit called Bohr magneton, abbreviated as Bm. The contribution to the magnetic moment from the spin moment of electron is called the spin only moment mu. It is numerically equivalent to 1.73 Bohr magneton. It is defined as 1 Bohr magneton is equals to Eh upon 4 pi mc. E is equals to charge of electron, H Planck constant, m mass of electron, c velocity of light. Mu s is equals to g into under root of s into s plus 1. S is spin quantum number 1 by 2. G is equals to gyromagnetic ratio. Gyromagnetic ratio G is the ratio of magnetic moment to the angular momentum. In case of free ion, the value of G is 2.0000023. For all practical purposes, the value of G is taken as 2. On substituting these values, we found mu s is equals to 1.732 Bohr magneton. Now, other forms of spin D is given. It is important to remember that the sum of the spins of paired electrons is equals to 0. If we considered both experimentally determined value of magnetic moment of some transition metal ion in good agreement with the spin only values. In some cases, the experimentally determined value have also been found to be larger than the theoretical predicted value. This can be attributed to the contribution made by orbital motion of electron in addition to the spin only value. Mu s plus L is equals to under root of 4s into s plus 1 plus L into L plus 1. S is resultant spin angular momentum and L is resultant angular momentum quantum number. The experimentally determined magnetic moment of some of the first transition series are summarized in table 2.2 along with the theoretical determined mu s and mu s plus L values. A close inspection revealed that the observed magnetic moment values are frequently greater than the spin only values mu s but are never greater than the mu s plus L values. It clearly implies that the contribution to the magnetic moments due to the orbital motion of electron is very small. It means the orbital moments are partially or completely quenched. This is primarily because the electric field of the ligand surrounding the metal ion restricts the motion of the electrons. Now, some problems are given. Orbital contribution to magnetic moment. We have already discussed that both the spin and orbital motion of the electron are sources of magnetic moment. The total magnetic moment of a material is then made up of two components called the spin and the orbital contribution. Both these contributions are due to the presence of unpaired electrons. However, in many cases, these unpaired electrons are the outermost electrons under consideration and are not screened by other electrons. In such cases, the spin contribution becomes important and the orbital contribution may be neglected. The most common example include ion of transition metals. On the other hand, when the unpaired electron lie well within the ions and screened by the outer electrons, as in true in case of inner transition metal, that is lanthanides and actinides, the orbital contribution cannot be neglected and must be combined with the spin contribution to give the total magnetic moment. The spin angular momentum of an electron does not depend upon the chemical environment. As a result, the spin moment of the unpaired electron is not perturbed by the changes in the chemical bonding of the compound. However, this is not the case with orbital angular momentum, which depends upon the chemical environment. Consequently, the orbital motion of the electron is very much restricted. This causes the orbital contribution to be reduced or quenched in the complex. This quenching of orbital angular momentum can be easily explained on the basis of crystal field theory. The unpaired electron in a first transition series metal ions are located in 3d orbital. A transition metal ion has 5 3d orbitals, all of which possesses the same energy and are degenerate. In order to generate the orbital magnetic moment, the electron should go around the nucleus via these orbitals. This is possible if all the three conditions are satisfied. The orbitals should be degenerate, the orbitals should be of similar shape and size, that is, they should be transformable into one another by rotation about some axis. The orbitals must not contain electrons of identical spin. In a crystal field, the degeneracy of d orbitals are split. For example, in an octahedral environment, the 5d orbitals are split up into two groups of different energy. It is this energy barrier that restricts the orbital magnetic moment of the electrons. It is important to note that also the set dz square and dx square minus y square orbitals are degenerate in the octahedral crystal field. Their shapes are such that cannot be transformed into the other by rotation. It means that the condition is not fulfilled. Therefore, the EG set of orbital cannot generate any orbital magnetic moment. Similarly, the E orbital set in case of tetrahedral complexes cannot generate any orbital magnetic moment. The T2G set of orbitals containing dxy, yz and zx orbitals can be easily shown to obey condition first and second. Consider the zx and dyz orbital in an octahedral complex. A rotation of 90 degree about the z-axis interconverts these two orbitals so that if an electron was initially in the dzx orbital, it could circulate along the z-axis by jumping between dzx and dyz orbitals alternatively. This movement is equivalent to the flow of current, which in turn produces magnetic effect. The circulation of current may be either clockwise or anti-clockwise. However, in the absence of magnetic field, the two possibilities are degenerate. When magnetic field is applied, the two direction of circulation possesses different energy that causes a loss of orbital degeneracy. In brief, dxy and dyz orbitals are degenerate, and the dxz orbital can be transformed into dyz orbital by rotating it through 90 degree about z-axis. Now it is the condition 3 that will dictate whether or not the T2G set will degenerate an orbital magnetic moment. Thus, an octahedral complex with D1 and D2 configuration fulfills all the three conditions. However, D3 electronic configuration does not satisfy the condition 3. Hence, D1 and D2 configuration will carry the orbital magnetic moment, but the D3 configuration will not. On the basis of above discussion, one can predict that the metal ions with electronic configuration D1, T2Z1 and D2, T2Z2 will have orbital contribution, but the complex with D3, T2G3 configuration will not contribute towards orbital contribution. Table 2.3 lists the electronic configuration of central metal ion in metal atom in which the orbital contribution is present or absent in high spin and low spin octahedral complexes with D1 to D9 configuration. Orbital contribution in tetrahedral complexes. When the metal ion is surrounded tetrahedrali by 4 ligands, the 5 3D orbitals split into two sets, T2 and E. The energy of E orbitals are lower than the energy of T2 orbitals. The three conditions the metal ions with electronic configurations are given will possesses the orbital contribution, whereas metal ion with the electronic configuration will not have orbital contributions. A comparison of the data reveals that in cases where no orbital contribution is expected, the magnetic moment value differ only slightly from the spin only value. This explains why tetrahedral nickel, octahedral cobalt and octahedral iron complexes, that an octahedral nickel complex and a tetrahedral cobalt will have the spin only magnetic moment. However, in reality such a complex exhibit a magnetic moment higher than μs. This is because the excited state of these complexes carry the orbital magnetic moment. In a system having such an excited state, the spin orbit coupling brings about some mixing of the ground state with the excited state, thus forcing them some orbital contribution. The magnetic moment in such cases can be calculated from the following formula: mu effective is equals to μs into 1 minus alpha lambda upon delta. Μs is equals to spin only moment, lambda is equals to spin orbit coupling constant, delta is equals to difference in energy level between ground and higher state, and alpha is equals to constant depending upon spectroscopic term. It is clear from the table that the value of lambda is positive from D1 to D5 and negative from D6 to D10. This clearly explains why the magnetic moment values determined in case of copper 2 complexes are larger, whereas in case of chromium 2 complexes are smaller than the spin only values. Orbital contribution in complexes of lower symmetry. We have already noted that the probability of orbital contribution is less if the symmetry of the complex is lower. In case of square planar or square pyramidal complexes, the orbital contribution is possible only in case of D2 and D4 configurations. In case of trigonal bipyramidal complexes, the orbital contribution will be observed in case of electronic configuration, that is D1, D3, D4 and D5. The orbital contribution of K in case of dodecahedral will be observed if the electronic configuration is D7 and D9. Temperature independent paramagnetism, TIP. A number of compounds are known that show a weak paramagnetism in spite of the fact that their ground state do not have unpaired electrons. Two such examples are provided by the permanganate ion MnO for negative and the hexaamine cobalt 3 ion CONH3 3 positive. Such 3 positives are overall charge. Such systems are not expected to show any orbital magnetic moment, are therefore likely to be diamagnetic. Since these species display weak diparamagnetism, it may arise by coupling the ground state of system with the excited state of higher energy under the influence of magnetic field. Because of coupling, the complexes may have some orbital magnetism large enough to cancel out the internet diamagnetism. Since this paramagnetism does not depend upon the thermal population of levels, it is commonly referred as temperature independent paramagnetism or simply TIP. Temperature independent paramagnetism TIP, likewise dimagnetism, is not due to the magnetic dipole within the molecule. Instead, it is induced when the substance is placed in the magnetic field. This induced susceptibility of the ground state is temperature dependent. The magnitude of magnetic susceptibility of TIP is of the same order as that of the diamagnetic substances. Thank you.